Hi, hello, welcome to Digital Electronics. Today I'm going to talk about the chapter 3 under Basic and Combinational Logic Circuit. I'm going to focus on the analysis of combinational logic circuit, design combinational logic circuit from Boolean expression, and also design a combinational logic circuit from the truth table. So the outline, I'm going to focus on 3.2, analyzing a combinational logic circuit. So in previous class, I already focused on the basic gates, 3.1. So there are 7 gates. So the NOT gate, AND gate, NAND gate, OR gate, NOR gate, exclusive OR gate, and exclusive NOR gate. So we're going to use mostly all of these gates to form a combinational logic circuits. So yeah, this is also the summary of the basic gates before. For the NOR gate, you have only two options, either 0 or 1. So you're going to have an output of 1 or 0. For other gates, the AND gate, 0 0 will become 0, 0 1 becomes 0, 1 0 become 1, and 1 1 become 1. So NAND gate will be exactly reverse of AND gate. So if you have 0 0 0 1, it will become 1 1 0 1 and 0. For OR gate, 0 0 becomes 0. Always don't forget it's an additional. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 1 should be 1. And the NOR gate is going to be reverse of OR gate. So you have 0 1 1 1. So you're going to have 1 0 0 0. For exclusive OR, whenever the input is same, you're going to have 0. So for example, you have 0 0, you're going to have 0. When you have 1 1, you're going to have 0. And 0 1 or 1 0, you're going to have 1 1. And exclusive NOR is a reverse of exclusive OR. So before this, same input, you're going to have 0. Now, same input, that is 0 0, you're going to have 1. And different input, 0 1 or 1 0, you can have 0 0 as answer. So combinational logic circuit. So what you're going to do over here is you have lots of gates. 7 basic gates. There is a different gates, and you are connecting each other. Just imagine like a Lego. So you have a few gates like this. This is 1, this is 2, this is 3. So you're going to have a connection of between these number 1 and number 2. So this is one set of Lego. This is another set of Lego, another set of Lego. So you're going to combine Lego 1 and Lego 2 together, for example, or maybe Lego 1 and Lego 3, you're going to combine together. So that will be forming a combinational logic circuit. So from here, you can get the Boolean expression to form truth table for that particular combinational logic circuit. So it's an example. So you have one gate over here. This is a gate NOR. Not. Going to have another gate over here. It's an AND. And this is exclusive OR. So you combine such a way like you have an input A is going to the NOT gate first. You also have an input A is going through to the one of the input of AND, and B is going through here. So you're going to have an output over here. So A is going through over here. You're going to have an output over here. Output of NOT and output of AND will be combined as an input to an exclusive OR. And you're going to have an answer over here. So this is the output over here. So when you combine more than one gate to form a combinational logic circuit, then you got the combinational logic circuit. So when you have like this, the truth table for each of the situation may change according to how you perform the connection, and also what kind of gate are you using for like I mentioned earlier. So when you have this one, so you need to run 0 0, so you have a 0 over here, 0 over here, and so on until you get the answer over here. So this is the output over here. So we will go through this in next slides. So you have a combinational logic circuit example. So let's say we have a similar circuit to example 1 just now. This is a circuit we're going to have over here. So you have a NOT over here, we have an AND over here, we have a exclusive OR over here. So A is going for the step 1. So you just analyze it. The way it should be is you analyze from left to right. So that means you have an input from the left to the output on the right. So in input for the first step is the NOT gate. So A is going through the NOT gate, and it will become from A become A bar. So you have an A bar over here. So write A bar over here. So A bar, you're going to have, so you just go through the same line and you're going to have an A bar over here as well. So that is marked as a red color. So next we go from the left, the next gate will be the below one. So from here you have a connection to A. So this A is written over here on the green color. So B, we have B over here. So A and B is going through a gate, AND gate. So the truth table for AND gate is when you have something, you're going to have this as an answer. So this will be the second step. And the second step over here is you're going to have A dot B. A dot B will become here is as an input. So you're going to have A bar on the top and AB on the bottom, and going through the exclusive OR gate. And the final, the step 3 will come A bar. So this is the A bar from here. So my bad. So I just bring over here. My bad, my mistake. So A bar and exclusive OR A dot B. So this will be your final answer. So step 4 is your Boolean expression X will be A exclusive OR A dot B bar. So let's go for the next one. So how are you going to obtain the truth table at X? So since you already have the Boolean expression, so you just bring the Boolean expression over here, the step 4. We go for the step 5. So you're going to run the situation. So only because of they have only 2 input, there will be 4 possible. There is 0 0, either you have 0 0 or you have 0 1, 1 0, and also 1 1. So in this case, when you run 0 0, so you have your first 0 over here. So the first step is to run over the NOT gate. So if you have a 0 over here, you become 1, and just return 1 over here. And then over here is still 0, so 0 is going down to the green. There will be a 0 over here, and B also, a B is 0, so you have 0 0. So when you go down to the gate, AND gate, you have 0 0, the answer will become a 0. So that's why you have a step 2 of 0 over here. So 0 is going here, and 1 0, when you go through the gate exclusive OR 1 0, you become 1 because it's a different input. So 1 0, you become 1 as an output. So that's then you put your step 3 answer as a step 5 answer over here, 1. So that is how you do for the input 0 A and B 0. You get output of 1. So you just continue the same similar situation. So you have a 0 1, and you have, let's say you have 0 over here, 1 over here, 0 is going here, 0 1, you're going to have a 0 over here because it's an AND gate. You have a 0 over here, it become 1, and 1 0 you're going to have 1. So you complete the second one, and then you do the same possibility of the third one. 1 0 is 0, and you're going to have a last one, 1 1. The answer will be 1. So just continue similar step. Okay, this is a self check. So you have 4 questions. So you have this is the first equivalent, so you can do on your own. And the second one is look easier. Yeah, you can have a look. Third one and the fourth one. The fourth one will be a little challenging. So, but I hope you can try and you can do it. So let's go to the document 3.3. This one is designing a combinational logic circuit from the Boolean expression. So earlier we have we have the circuit, we have the diagram. So now we're going to design a circuit, a combinational logic circuit from the given Boolean expression. So how are we going to do this? So there are few steps. So first you need to group up the variables in bracket or in a big group. So I will go through on this one, just accept first. Then you need to identify the main and or the sub operation. So this usually come with the experience. So as more you do the examples, you will know, you will be more comfortable. And last not but least, it will become the drawing the input. So you need to draw what we have. So let's say we have an example. So this is the example 2, designing a combinational logic circuit from the Boolean expression. So you have a Boolean expression. You have a Boolean expression. So you have x equals to a dot b bar dot c plus b dot c bar plus c, a big bar covering all this. So you have a question like this. So first you need to read from the left to right. So you have this one and identify the operation involved. So over here it will be, if you have a dot, is always focusing on the, so let's you focusing on the operation of and plus is always or. So you just focus on that. So next, when you already identify the operations, so we don't have a exclusive over here, so it's a great help. So we go for the second step, is to so now we focusing on the bar. So you have a big bars, so that is a very good one. So first one, bar is always helpful, so please take note on that one. And deal it with it. Okay, for example, the first one, you have a b bar. So because it is alone, you cannot do much over here, so just leave it first. And then the second one, so you have a bunch of bars. You have a 2 input with 1 bar sharing 1 bar, and 3 inputs sharing 1 big bar. So what you do is you just focusing the one particular group as 1 bar. So this is one group. So you have a one group, a big like this, and then this particular group will have another big group with the C, such like this. So just, so if you have a question like this, or you have going through this one, I like to use drawing method. So you just draw a big circle on B and C over here, the bar, and a bigger circle on the plus C. So you look like this. Next, we go for the third step. Consider operation that if might be able to be grouped. So this one is settled, so nothing much, follow back. And we're going to have a dot b bar dot c plus. So how are you going to do this? So for example, because this operation are the similar operation, so you have 2 times of and 1 is or, so you just go with the bigger one. So you group up this one to become another group. So this is coming with by experience. So yeah, you need to go through this a few times before you understand. So we go for the step 4. So we identify the priority operations. So you're going to have, you already selected the third group. So you have a first group over here. So I put it over here, first group. The second group is the blue color. So the third group will become the pink color, and the fourth group become the whole thing, which is operation of all. So that is the priority of operation. So next we're going to draw it. So the step 5 you're going to draw. So you draw the group 1. So you have the group 1. So b dot c bar. So this is more too similar to the AND gate. So you're going to have such a way. So this is the first one, the red color. So if you go for the second one, the second group, you're going to have a AND gate, which is also with the NOR, with the OR of the C. So you come up with the C over here. You have the group 1 over here, and you have the NOR gate because it have a bar. So this is the second group, group number 2. And then you're going to have the group number 3. So you have A dot B bar dot C. So your B need the NOT. So you're going to have a NOT over here. So B is going to the NOT first. And then you're going to have the AND gate. So you're going to have an AND gate of A, B naught, and C. So if you really look over here, you're going to have a 3 input instead of 2. So this is possible. For the digital electronic, it's possible to draw 3 inputs for one particular. Even there are some cases until 5 is okay. And then group 4, so you're going to blend the group number 2 and also group number 3. You see over here, this is number 3, this is the group number 2. So you're going to blend group number 3 and 2 together. So you come up with a group number 3 over here. So this is group number 3, and you're going to take up your group number 2 over here, and then combine both of the outputs to be to the one OR, and you're going to have the final answer of z or x over here, right? That's all. So this self checkout number 2. So yeah, you're going to have such a way. So this one is be careful with the XOR. And second one is looks very easy. So you should already figure out this one. If you go for the basic gates, you will already understand. The third one will become little challenging because they have bars, and also they have a XOR. And fourth one and fifth one is optional. It's a very challenging one because I just put lots of gate brackets, sorry, lots of bars. So it's a very challenging. Try to get this one if possible. So we go for the document 3.4, which will focusing on the designing a combinational logic circuit from truth table. So before this, we are focusing on the Boolean expression. We have the Boolean expression, we draw the combinational. Now we're going to draw the similar combinational logic circuit but using truth table. So previously, what we have done, we have a circuit like this. So you have a b c as an input. So going, so you have the circuit. So you have a NOT, you have NOT, second NOT, you also have on and or and so on. So to do this, you have to go through, okay, a is going through here, become on, become a bar. So you have a bar over here, so I put a bar over here. So the second one also b is going to odd, not, so it's going down over here, it become b bar. And c is from the c itself, not or not, so it becomes c. So because this is a okay, okay, it should be this one, should be, yeah, this also this one, I'm sorry, my mistake. So it become a bar dot b bar dot c. This one become a dot b bar dot c bar, and a dot b dot c. So when you have all over here, you're going to combine everything in a addition. So a bar b bar c. So you're going to have only addition with a dot b bar dot c bar, addition with this one a dot b dot c. So this Boolean expression have we obtained from the combination logic circuit diagram. So how about from on the truth table side? So from this one, because they have three types of input, so you're going to have three, eight, 3 to the power, 2 to the power of 3, you're going to have 8 possible, which is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So the input is A, B, C, and you're going to have 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this is the truth table. It's a possible truth table for 3 inputs. So each of this situation, when you have 0, 0, 0, is actually is a bar dot b bar dot c bar. And then over here, uh, don't forget, this one is also 0. And then you're going to have, for this one, 0, 0, 0 become a bar dot b bar dot c. 0, 0, 1 become a bar dot b bar c, and so on until you get 111 equals to a dot b dot c. So this is the response of each situation of input A, input B, and input C. But we cannot use everything. We need to know which one is going to be activated. So that one is depending on a situation where, let me finish this one. So it's depending on the output over here. So for example, we will select the output 1 over here, which one is 0, 0, 1 become 1, 0, 1, 0, 0 become 1, and 1, 1, 1 become 1. Why I select this one is because A bar, this is A bar, this is B bar, and C. So this is equal to this one. So that's why we select as 1 over here. And this one, A dot B bar dot C bar. So you can see over here, A dot B bar, C bar, and also you're going to have a dot b dot c, which is similar to this one, a dot b dot c. So that's why you select this as 1, over here is 1 and 1. And other than that, because it is not selected at all, it becomes 0, 0, 0, 0, 0 over here. So either this is given, or usually is given based on the circuit, or maybe there is a situation why you need to select this one. It depends. So two table, because this is from two table, so this is should be given. So so we go for the next one. So you already have the output 0, 1, 0, 0, 1, 0, 0, 1. So this is similar to the previous situation. And for to determine whether it's going to be okay, for before I'm going this one, I just put it over here, shorthand writing, which is M0, M1, M2, M3, and so on. So to determine whether you're going to select sum of product or product of sum, you have to depends on this particular output. For example, if you are determining for sum of product SOP, so you're going to have a SOP, you have to focus on the output, which is 1. So like I mark it on pink color. So it's 1. So we're going to use OR gate to express. For example, So to make it easier, so I put it over here, M. So you're going to focus on M number 1, M number 4, M number 4, and M number, my bad, this is 7. It shouldn't be 7. So so when you expand this particular shorthand writing, you're going to have A bar B bar C plus A plus A B bar C bar plus A B C. So that's why you get this particular equation, Boolean expression. Then later on you can draw from here, become a combinational logic circuit. For the POS, which is the second one, the product of sum, so you're going to focus the output of 0, which is the reverse of the number 1. So 0 0 0, so you have 1 2 3 4 5. So you will put over here this is a symbol of POS. So you're going to have 0, you're going to have number 2, you're going to have number 3, you're going to have number 5, and you're going to have number 6 over here. Then this response is from here. So A bar, B bar, C bar. So you're going to have a number, because this is a inverted POS. So A bar plus B bar plus C bar dot A bar plus B plus C bar, because we are going to use N. So A bar plus B plus C and A plus B bar plus C and A plus B plus C bar. So that is the final answer for the POS. So usually in our situation, we always use the SOP rather than POS. So just for your information, so we always have the POS SOP as our final answer. So self-check number 3. So you have given a truth table. So try to get the Boolean expression and the combination logic circuit. So you have the output X and you have output Y. So you need to go through one by one. So you have 3 inputs for the X and 3 input for the Y. So just follow the previous steps. So you're going to get the answer. And just follow and get the SOP. The second one will be a little challenging. This is a situation. So you need to design embedded safety kit seat. So you have 3 inputs, which a sensor, 3 types of sensor: input A, input B, input C, and you have 2 output, M and N. So sensor A was placed at the bottom seat over here. So before this child is sitting on the sensor sensor A, and then sensor B will be put it on the headrest. So the head will be covering the seat sensor B, and sensor C will be the buckling clip. So whenever you plug in, you become high. There is 1 when there is a press or tugging. So for the output M, it will become high. Okay, this is the situation. We wanted to have output M will become high when both of the input A and B are high. So when you have a high over at the A and B, so your M will become high. And input N will be high when the input C and input M is high. So you need to obtain the truth table and its equivalent combinational logic circuit for M and N. Please use the SOP form to perform this situation. So next we go for the this is the end. So next we should focus on the Boiling theorem, which is coming next video. That's all. Thank you. Have fun.